Okay, welcome back. I'm going to now work through a example problem for conjugate beam. This will be our first example problem, and then there'll be links to 3 or 4 more other ones, and then you can check the website for homework due for next week. So let me go back and share my screen. And here we go. So let's start this example problem. Okay, so the first problem we're going to do is we're going to find slope and displacement at point C for this beam. So this is a simple supported beam, really a fairly easy problem for conjugate beam, as you'll see in a second. So we'll work our way through it. What's unique about this too is this is the first time we've actually got or have values for E and I in the structure. Now, before we do this, let's just think for a second where we are so far. We only have 2 methods right now. We have conjugate beam and direct integration. If I were to work this problem with direct integration, I would have to write 2 sets of moment equations, one that's good from 0 to 10, and then a second one from 10 to 20. And then I'd have 4 integration constants to do. Not a hard problem, but definitely one that's fairly challenging. So let's see how conjugate beam handles this. Again, we're only looking for the value of slope and displacement here at the center. So remember, the first thing we need to do is find the moment diagram. Now I'm going to shortcut this a little bit. I'm sure if I gave you enough time, you would be able to come up with this moment diagram on your own, but I'll just go ahead and draw it for you. So the moment actually at the middle of the beam is 50 kip feet, and we're dividing by EI. You can see here, there's the maximum value. Now, a lot of students ask me, hey, I can go ahead and divide 50 by EI and then away I go. Well, I would discourage you from doing that because you'll notice that the numerator is 50 and this denominator value is quite large. It's 30,000 in this case times 300. This number is going to be so small to carry around that you're going to end up losing through round off and truncation. You're going to lose some accuracy. So I'm going to encourage you to keep EI in the denominator and carry it around to the very end. Also, in some problems, I don't give values for E and I. I just say EI is constant. So your final answer will be some value over EI, and we'll talk about that in just a second. All right, so now I have my M over EI diagram, and I'm going to build my conjugate beam. So you'll notice that our external pin maps to an external pin, and the pin at B maps to a pin at B. So there's my conjugate beam. So in this case, pretty simple. But now on that conjugate beam, I'm going to apply moment divided by EI as load. So you'll notice my moment is positive everywhere. So I have a positive load, and positive load is up. So at this point, you've made the transition from the real beam to the conjugate beam, and really half the problem is done. So now I'm just going to take the conjugate beam itself, and I am going to find shear and moment in the conjugate beam. And remember, shear in the conjugate beam is slope in the real beam. And moment in the conjugate beam is displacement in the real beam. So really, I've just turned my problem into something abstract where in this new space, the conjugate space, I can do my shear force and bending moment diagram techniques just as before. So let's begin. I'm going to first find the reactions in my conjugate beam. So there's my conjugate beam, or I could just have given you this problem, except it has these strange units here for the loading. We'll talk about that a little bit later. So the first thing I'm going to do is look at my reactions at A and my reactions at B. So I'll assume they're both up. I find the concentrated equivalent load for the distributed load, just as we've done before. It's 1/2 base times height, except it has little interesting units. Before I do that, you'll notice now that the force in the conjugate beam is kip feet feet. So that's just going to be kip feet squared. So got to keep track of these units as we go along. So I'm going to sum moments about A. So I've got, there's my force, 1/2. And then that's the force. And then there's my distance. And then force By and distance. So I can find my reaction By. In this case, it's negative. So it's actually down, which makes sense. My forces are all going up. So you'd expect my reactions to be down. And again, notice the units again, kip feet squared over EI. I'll come back to that in just a minute. Okay, I can sum forces now. And you can see I got my concentrated equivalent force acting up. And of course, AY and BY are also acting up. I have BY, so I can solve for AY. And it's no surprise that it's the same value. Now remember, what I want to find is the value at point C. So now I need to come back and cut the structure at C and find the internal shear force and bending moment at C, so I can work either the left side or the right side. So in this case, I decided to work the right side. So I cut the beam, looking at the right side. There's my positive shear force at C. There's my positive bending moment at C. I just have to find those. So I begin by applying my reaction at B. Remember, it was negative, it was down. So now I'm going to sum moments at the cut, long expression. But again, you can see there's the force of the distributed load. 1/2 base, 10, times the height. Remember, 50 kip feet divided by EI. And then that's the distance to the centroid. 1/3 the distance from the cut, or 10/3. And then my reaction force, it's down, so that's creating negative bending moment about the cut, and then there's the moment arm. So I'm solving for the moment at C. So I do that, and I get this. Now notice the units of the numerator. So I have kip feet squared times feet. So each of these terms are kip feet cubed. Now let's take a second and think about it. What are the units of E and I? Well, E, let's see if I can write on this thing. E is force per length squared. And of course, I is linked to the fourth. So EI will have units of length, of force length squared. So I got force length squared in the denominator, and I got force length cubed in the numerator. So when you check those units, you end up with length. And so the moment in my conjugate beam ends up with units of inches or meters, which is, remember, moment in the conjugate beam is deflection in the real beam. So now I can go ahead and divide by my actual value of E and I, convert from cubic feet to cubic inches, and now I'll have dimensions of inches, and when I do that calculation, I end up with a negative 0.32 inches. So that's the displacement at C. The negative means it goes down, which makes sense from the original beam, and we have an actual value. One thing to think about here as a designer, now that I have a value for my displacement, I can think about limit states. What if my displacement was limited to 0.25 inches? Well, this is too much. So how do I decrease displacement? Well, I can't change the moment, I can't change the length, but I can change E and I. Now, E is usually associated with the material, in this case, steel. You're probably not going to be able to change that, but you definitely can change I. So increasing I decreases displacement. So that becomes your design criteria. So when you get into design work, you are selecting cross sections based upon their I value and other parameters to not only look at stress and strain, but also displacements. Okay, we have one more thing to do. we need to find the slope, and that comes from shear. So I'm going to sum forces in the y direction this time. So again, I have this is my concentrated equivalent force of the distributed load. And then, of course, you have the reaction. And then the unknown shear. So when I solve for the shear, well, the shear comes out to be 0. Now remember, shear in the conjugate beam is slope in the real beam. So that tells me that the slope at the middle of this beam is 0. That kind of makes sense. If you remember our original beam, we had a 20-foot long beam, point load at 10 feet. And we're asking for the displacement in the middle. We just found it, 0.32 inches. And it says now the slope is 0. Remember, 0 slope usually means your curve is max or min. In this case, it would be a maximum displacement. So there you go. Pretty simple application of conjugate beam where we found displacement and slope at a point. So I'll end here. And then if you check on the website, you'll see 2 or 3 other worked problems. And then check the website for homework. So I'll come back and let me know if you have any questions. Again, email me if you have a problem or give me a call. So until next time, take care.